biodegradation of plastics. Plastic waste has become a global environmental concern due to its durability and resistance to natural breakdown. However, in nature, certain microorganisms, including bacteria, fungi, and algae, have evolved to decompose plastics. This process is called biodegradation. Biodegradation is a biological process where microorganisms break down plastic polymers into simpler compounds. This occurs in two main stages. Fragmentation, UV radiation, heat, and mechanical stress weaken the plastic structure. This breaks down longer polymer chains. Microbial deposition. Bacteria and fungi secrete enzymes that digest the smaller fragments. The process converts plastics into components such as carbon dioxide, water, methane, and biomass. This is called mineralization.
Three main biological agents that are capable of processing plastics: algae, fungi, and bacteria. Bacteria are the main organisms that secrete specific enzymes depending on the species and the plastic, and are, of the three, the main subject of research. But fungi show great promise, as there are many species which attack many plastics, such as Agamonium chilense attacking polyethylene, and Aspergillus japonicus and nocus attacking low-density polyethylene. Enzymes are biocatalysts that allow bioreactions to occur in organisms. For example, alpha amylase in humans, which catalyze the breakdown of carbohydrate starch. Now, here's a case study on the bacterium Ardionella sakiensis, which was found in a Japanese Suez Center in 2016, and it was found that it could break down the plastic PET, which is a very common plastic, using plastic bottles. Now, this is the reaction pathway for the case study, which occurs in two stages. First, the PET monomer is broken down by the enzyme PETase into two molecules, B het and M het. Now, in the second stage, the enzyme metase hydrolyzes the ester group here, and it breaks the molecule down into two, PPA and EG, ethylene glycol and terephthalic acid, which can then be used to make more PET.
Biodegradation is a promising answer to the myriad issues posed by microplastics. Microplastics can contaminate soil, impacting both physical and chemical properties of the soil. This also affects plant life that grows from said soil, and thus crop quantity and quality, causing economic issues for agriculture. Humans consuming contaminated food will in turn store microplastics in their bodies. This has been linked to increased risk of cardiovascular disease, hormone disruption, and GI issues. This knowledge of biodegradation can be applied on an industrial scale to capture and repurpose microplastics before they can cause environmental harm. The textiles industry is a significant source of microplastics. Bacteria in these processes can be genetically modified in order to produce a greater quantity of enzymes. Chemical engineering practices allow for optimization of reaction conditions and therefore the extent of reaction.
Biodegradable plastics like polylactic acid, PLA, and polycaprolactone, PCL, can be produced by enzyme-reliant processes such as fermentation and enzyme polymerization for PLA, or using enzymes as a catalyst in PCL. This helps make these processes cost-effective because renewable resources are used and cost less energy as the enzymes are catalyzing the reaction. Biodegradable plastic can be put through microbial and enzyme-driven waste treatment, which is beneficial, as this is a circular economical system, meaning byproducts can be commercialized, such as the nutrients and sludge for agriculture. It reduces the use of finite resources like fossil fuels and incinerators, releasing less greenhouse gases, and produces energy from waste, making it a partially self-sufficient system, which is very valuable to chemical engineers. Thank you.